All right, I'm hoping this is a quicker walkthrough video for these notes, just to kind of go back and give you guys something to study with. One of the 4 or 5 things we talked about in this lesson was vertical asymptotes or removable discontinuities, so we can call those holes. Vertical asymptotes occur when at the x values that make the denominator 0, because we can't divide by 0, so that's going to create a vertical asymptote in our rational function. And if we factor and simplify the fraction or rational function and a factor cancels out, then that x value is called a removable discontinuity or a hole instead of a vertical asymptote. And it's going to look something like this. Now remember, visually this is not going to show up on a graph on Desmos or in your calculator because it is so infinitesimally small. You have to know it's there so that you don't include 3 or whatever the hole happens to be in your graph. So in example 1, we're going to find the vertical asymptotes or the hole and factor first. So we take the first rational function here. This is the difference of 2 squares, so we're going to factor. And nothing cancels out, so we can automatically say that we have no holes in this graph. But we have 2 vertical asymptotes, because if I plugged 3 in here, 3 minus 3 would be 0, and that would make the denominator 0. And negative 3, because if I plug negative 3 in here, it would give me 0. Again, for B, we're going to factor first. We have the difference of 2 squares again, but this time, these 2 factors cancel out, which means we have a hole at that particular 0, which is x equal to negative 3. There's going to be a hole in my graph just there. But once we factor that out and cross out the things that cancel, we're still left with f of x equal to 1 over x minus 3. So my denominator, still make it equal to 0 and solve. My vertical asymptote would be at x equal to 3. For letter C, nothing factors, so nothing would cancel for this one. This is the sum of 2 squares, and we have no pattern to factor the sum of 2 squares, only the difference. So if we're trying to find the vertical asymptote here, we would set the denominator equal to 0 and then solve. But when you solve this, you end up with plus or minus 2i, which means that we have no vertical asymptotes, because an imaginary number is not a vertical asymptote on this real number line that we're graphing. So these are real numbers, and we're not going to graph imaginary numbers on a real number line. Second thing we talked about is horizontal asymptotes, which in regards to these sorts of things, it's also our end behavior in regards to rational functions. So the acronyms that we're using in this class are BOBO, BOTN, and EATS DC. Those 3 acronyms are going to help me find the horizontal asymptotes, which means we're finding our end behavior. BOBO stands for bigger on bottom, which means my horizontal asymptote is at y equals 0. BOTN, bigger on top, means that there is no horizontal asymptote and that the graph is going to positive or negative infinity. EATS DC, exponents are the same, divide coefficients. So our horizontal asymptote is at y equals whatever the numerator coefficient divided by the denominator coefficient would be. We've done this before, so hopefully it should start to feel a little solid for you. We have our horizontal asymptotes, and this again tells me how the graph behaves at positive and at negative infinity. It's going to get very, 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 very close to that particular line, but never touch it since it's an asymptote. So if I ask you to find the horizontal asymptote or the end behavior, all you're needing to do is match it up with BOBO, BOTN, or EATS DC. This first graph is bigger on bottom, its bigger exponent is on bottom, so it's going to have a horizontal asymptote at 0, which means we can write it as a limit statement. It doesn't say to do that in the instructions, but we're going to do that for good practice. We're going to say the limit as x approaches both positive and negative infinity, so as we go to the right and to the left, that function is going to converge on the number 0. B is bigger on top, which means we do not have a horizontal asymptote. So the limit as x approaches positive and negative infinity is infinity. The limit does not exist, basically. F of x equal to 3x plus 4 over 2x minus 1. These exponents are the same exact degree, so we're going to divide these coefficients. The horizontal asymptote is at y equals 3 over 2. Which is the limit statement. As x approaches positive and negative infinity, f of x approaches 3 over 2. On the back side here, we talk about something new called slant asymptotes. So slant asymptotes are truly the end behavior still for these graphs. It's how the graph behaves as we get to positive and negative infinity. But it's not a flat line, it's not a vertical line, it's some sort of sloped or slant line. Some people call these oblique asymptotes. We're going to call them slant asymptotes. This occurs when the degree of the numerator is 1 more than the degree of the denominator. So what I'm going to start writing places is that it's bigger on top by 1. Instead of bottom, it's bigger on top, yes, by 1, which means we don't have a horizontal asymptote, we now have a slant asymptote. To find the equation of the slant asymptote, and it's going to be a y equals mx plus b equation because it's a slanted line, we have to divide long or synthetic to find the slant asymptote. But we really don't care about the remainder, so you actually don't have to finish all these problems because we don't care. Remember, you can only use synthetic division when the divisor or the denominator is in the form x plus or minus c. So if there's any sort of squared, if there's any extra stuff going on, it's not just x and some number, you're going to have to use long division. So if you look, you can use synthetic, have to use long division, might have to use long division. Okay, let's try number A together. I'm actually going to show the work on this one. So we want to find the slant asymptote. Because this is in the form of x minus c, we know that c is equal to 1. And we can use synthetic division. The dividend is 1x squared, no x's, and 1 coefficient of, or constant of 1. Bring down, multiply, add. What am I doing? Multiply, add. Remember, we get the remainder, the constant, and the x term. But again, we don't really care about the remainder, so don't care. And this tells me what's left over. This part right here is my slant asymptote. It's the equation, the quotient here is the equation of the slant asymptote. So letter A has a slant asymptote at y equals 1x plus 1. And you can graph this and see. When you graph this, there's going to be a invisible diagonal line, and you can type this in too to see that it happens, that comes infinitesimally close to what we started with here, but never touches it. And it's diagonal, it's not horizontal or vertical. Number B, hopefully you notice that because the denominator is not x plus or minus c, we are going to have to use long division. And those steps are divide, multiply, subtract, bring down, repeat. And let's do that slowly. I'll use a different color so you can kind of see what I'm doing. So we're going to have x squared minus 5x plus 1 as my divisor, and 3x cubed minus 0x squared, because we're missing x squared terms, minus 2x plus 6. We're going to skip down to what's less than the 2 powers I have. I have a power of 3 here, and I have a power of 2 here. So that means I'm going to write my first term here. Okay. We divide just the first ones. We divide 3x cubed divided by x squared, and I'm going to get 3x. Then I multiply that 3x times every single part of my divisor. So 3x times x squared, 3x times negative 5x, 3x times 1. It's like distribution. We'd get 3x to the third power, negative 15x squared, and positive 3x. Now that's divide and multiply. I'm going to subtract. Remember, subtracting is just like adding the opposite. So if I go in and change all these signs, I now can add the opposites. First terms should cancel, and if they don't cancel, you've done something wrong. Negative 0x squared. Why did I put negative 0x squared? Could be positive 0x squared. I digress. Okay, so we subtract, we bring the 6 down, and we repeat. We are dividing the new biggest part of my dividend. I'm using air quotes, you can't see me. Divided by x squared. We would get 15. Distribute. 15 times x squared is 15x squared. 15 times negative 5x is negative 75x. And 15 times 1 is positive 15. But all of that, I'm going to subtract. And subtracting is adding the opposite. First two should cancel. And really after this, we don't care. You're going to get 70x minus 9, but that would be my remainder. And like, again, we don't really care about the remainder. What we care about is the dividend that we got. That dividend is going to become my slant asymptote. Y equals to 3x plus 15. That's the y equals mx plus b line that this f of x, this function, would get infinitesimally close to as it goes to positive and negative infinity, its end behavior, but never touch. And last but not least, if we look at number C here, and we try to find its slant asymptote, we're going to run into a problem. Because remember, slant asymptotes only occur when it's bigger on top by 1. This is not bigger on top by 1. In fact, this is bigger on bottom. So it's going to have a horizontal asymptote at y equals 0, but it's not going to have any slant asymptote. Okay, only have a slant asymptote only when bigger on top by 1. That's when you have a slant asymptote. Otherwise, you have some sort of horizontal asymptote like this one. The last section on these notes is about the limits of rational functions, and we need to get really used to the way that limits are written. This first limit is a little bit different. We've actually seen this a little bit before. The limit as x approaches a from the left is how you say this, from the negative side. The limit as x approaches a from the positive side, or from the right. Then we have the limit as x approaches negative infinity, and as x approaches positive infinity. That's our end behavior on the left side and on the right side. But these new limits, as we approach a certain number from the left side and the right side, are really interesting when it comes to vertical asymptotes. Now, of course, all of the work is already written in here, I know, but let's just talk about it for a little bit. The first one is purple. It says the limit as x approaches negative 3 from the left. So we find negative 3 on the x-axis, so it's x getting close to it. Obviously, there's a vertical asymptote there. But as we look down and we get close, okay, on the left side, what's happening to that graph? It's going towards negative infinity. But on the right side, that graph is going up to positive infinity, which is very interesting. So our limits are opposites. It's going to help us graph later if we know what's happening on either side of these limits, if they're going to the same togetherness or they're going apart. These limits are very important. The next one says the limit as x approaches 2 from the negative side. Here's 2, and again, we have a vertical asymptote, which is why we're really wondering about the limit. And on the left side, so as I'm getting close to 2 on the left, this graph is going up to positive infinity. And as I approach the limit of 2 from the right side, so from the positive side, this graph is also getting close to infinity. But the limit as x approaches negative infinity, so left end behavior, if you're looking at this graph as it goes to the left, it's getting closer and closer to that horizontal asymptote of negative 2. So the y values are getting closer to negative 2. Same thing should and does happen on the right side. As x approaches positive infinity, it should converge on that same horizontal asymptote, and it does, negative 2. Limits are very cool, but they're a little confusing because of the way that you read graphs on these left side and right sides. Remember, left side is the negative, right side is the positive.